Hello, this is James Santiago for North Central University, and I'll be presenting database model design and use. Now to start off, before I even define what a database model is, I should probably define what a database is. For this presentation, database that we'll be referring to is the tabular sense of a database. In this setup, we have a database that contains many entities, and each entity is defined by its properties. An entity, for example, may be, let's say, a student, and the properties of that student may be first name, last name, grade point average, and so on. And inside of that entity, we may have several records. And a record we can refer to as either a row or a tuple or even a record. In each record that we have will have multiple columns, and those columns will represent the properties of that entity. And each property of this entity will also have a data type. Data type may be something such as a string value, an integer, or a float value that defines the type of data stored within that column or property. Now we take this a step further with the database model by defining the relationships between those entities. This can be especially important for certain database systems that require a certain level of integrity on the data that it contains and a certain level of logic and constraints on the operations that occur on that data. So for example, we may have a financial system and we want to make sure that we have transactional safety on that database. So when one entity is updated and our transaction defines that after that entity is updated, another entity must be updated, our relationship may say that if the first update fails, then the entire transaction needs to be rolled back. That's something we may define as part of the database model. Now the first database model we'll be looking at is the hierarchical model, and it's defined by a tree-like structure where each entity may have many children entities but only one parent entity. So as you can see in the example we have here, a student may have a child entity such as a course, and that course entity may have another child entity called the grade entity, but the grade entity may only have one parent entity. This may be a problem for certain real life models. Using the hierarchical model may restrict us from modeling certain types of data, but it still can be useful in a performance and specific application use sense. One thing that we can do with the hierarchical model is easily recurse through each entity by only having to define two operations. The getParent and getChildren operation can easily be used over and over to effectively recurse through every entity in a dataset. It's pretty useful for certain types of applications, such as defining XML and JSON type data. The next database model we'll look at is the network model. It's similar to the hierarchical model in the method that it defines relationships between entities, but the difference here is that a child entity can have multiple parent entities. So we have a many-to-many relationship between entities. This can be especially useful in extending the types of data that we can model. Certainly a lot of real-world data can be modeled using this method. And it's actually used today in an extension of this model, which is the graph model. We can see this used to model data such as transportation networks, where a city might have multiple roads leading out to other multiple cities, and those cities may also have multiple connections to other cities. Can be very useful in specific data modeling methods, but we are restricted to how the relationships are defined. We can't define specific relationships, such as saying that one city may only have one relationship to another city, because we're defining, say, interstate highways. For that, we'd want to use the relational model, where we can explicitly define each relationship between entities. This is most closely representative of real-world data. For example, in our student example, we can say that a student can have multiple classes, and a student may have multiple books, but that a specific book entity may be owned by only a single student. And by a single book entity, I mean a unique book, a real-world physical copy of a book. And you'll see the relational model in most database management systems. It's very extensible, very easy to model a wide range of data, and it's a very mature database management system that uses a lot of optimization techniques to get over some of the modeling shortfalls that relational model has. And one of those techniques that the relational model benefits from is the ability to use normalization. Now, normalization is defined by how the properties of an entity are related to other properties within the same entity. So, for example, our student entity may have a data property that says the field of study. So record A may be John Smith, who is in the field of study of computer science, and record B may be Jane Smith, who is also in the field of computer science. Now, in this entity, however, since you're defining the field of study directly in the student entity, you have a redundancy of data. So each time you define the field of study that's the same as another record within the same entity, you're duplicating the data. Normalization comes in by saying that this relationship between properties within the same entity needs to be separated into its own entity. So the field of study would need to be taken out of the student entity, placed within its own entity, and instead of defining that field of study value directly within the student, you would define a relationship between the student and the field of study. This allows you to reduce the data redundancy. We no longer have to define the field of study multiple times when it's the same. So for our record of Jane Smith and John Smith, they would simply be have a relationship to the computer science record within the field of study entity. And this can allow us to have a consistent set of data. I mean, before, when we didn't normalize our data, that field of study may have a problem where we accidentally mistype, say, the computer science, so that Jane Smith is in the field of study of computer science, and John Smith is in the field of study of computer sciences, where we wanted them to be both in the same field of study. Now we have inconsistent data. But if in our scenario where we normalize that data, they would both have the proper field of study name, and if we ever wanted to update it to, say, computer information science, we would simply have to update that single record and not have to update multiple student records. Now there's different stages of normalization, and they're defined by the relationships within the properties. The relationships can go to a high level of normalization such that you'll never have any data redundancy. But unfortunately, there's a side effect of using normalization, and that occurs with database performance. So when we have these multiple entities and we want to query that data, we have to join it together. And those database joins can be very expensive on performance when we start to work with large data sets. So what can be done is denormalizing the data. In our example, we may want to avoid separating that field of study entity and keep it within our student entity, and then rely on, say, the application level or additional rules to ensure data consistency. Now the last model we're going to look at is the object-oriented model. Now object-oriented refers to the object-oriented programming system. Here objects define the entity within the database and can benefit from many of the capabilities of object-oriented programming, such as inheritance and extensibility. Now, when I say inheritance, that allows you to define let's say a base class, such as a student, and you may have, say, subclasses that may benefit from inheriting the student entity, such as a lab student. Lab student may have properties specific only to that lab student, but they can inherit the student entity so that they can they can utilize the same data without having to replicate that data and functionality down to the lab student entity. This model is often defined in many programming languages and extended through certain frameworks such as LINQ, and that's used in .NET, and Corba that's used in Java, to allow you some level of database functionality within the programming language itself. There are some advanced models that extend the models that we looked at so far. For example, the GIS model can be used to define geological information systems. The relational model actually can be used to define this system, but it's often extended to allow for specific data types and specific functionality. For example, in a GIS model, you may have a line and point data type that allows you to perform define certain geological structures, such as a state boundary or a road, for example. And operations may exist within the GIS model, such as being able to query if a point exists within a geographic boundary. So for example, I may be able to query a GIS database to figure out how many cities exist within a certain state. Another advanced model is the object relational model. This can be in either your hierarchical network or relational database, and is defined by specific data types. It's similar to what the GIS model does. It extends existing models to use advanced data types, such as a video file or a sound file, and then be able to perform query-related operations on that data, such as finding a specific point within a specific movie, for example. And the last one we have here is the ontology model. This can be seen as kind of an abstract layer above other models. We can kind of see this in database warehouse software that uses a wide range of models in query languages to combine data into a single data set. And the ontology itself is a method of defining everything about a area of knowledge. So the ontology might contain multiple data sets, multiple models, and have it constructed in such a way that it fits within the ontology. Now, we talked about normalization for a minute, and the part about denormalization can be something we may not want to do. Normalization offers us a lot of important functionality and allows us to define certain transactional safety and certain data integrity functionality within our database. So we may want to use a second level or additional system in addition to our database model to perform these operations and to improve performance above the relational model. One of those can be through the use of views. Now, a view is defined within a database management system as a predefined query, which may be something like joining several tables. So we may see like a student view where we join the students with the field of study entity and also join it with a few other entities into a single table view. Doing this may allow our database management system to define optimizations ahead of time by being able to predict what data that is being looked for by the querying agents. So the view can be used to denormalize data on a already normalized data set. Useful if it needs to be viewed a certain way, and of course you can get some level of optimization from the database management system. Another system is key value caching. This can often be seen in application level and also in certain programming languages. So we may have systems like C#, for example, which can define a list or a hash value collection and store data from a database so that you can query it only once, denormalize the data, and then interact with it and present it to the customer as a sort of middle tier operation between the database and the user interface. And some databases are starting to advance with the availability of larger amounts of system memory and lower cost of system memory, such as Microsoft SQL's OLTP in-memory database tables. On these setups, they have your relational database system existing entirely within memory. And doing this allows you to do certain operations which couldn't be done with persistent memory, such as updating a table record without performing a lock on it, which can have significant low latency database update and retrieval performance gains. We also have application-specific models, such as document-based, seen in NoSQL database management systems, and also full-text search models. So as we said before, relational models can be used to define just about any real-world data model. But unfortunately, we may see that the performance isn't linear. We're not going to see perfect performance with all types of data models. So we see the emergence of these application-specific models where they benefit from performance gains of where they focus solely on certain types of data models. So for our document-based model, we see certain software like Google's Bigtable, where they store wide columnar data within their own distributed file system. And we could also see this in XML and JSON file storage, where a database is structured within a single text block or text file and then retrieved one document at a time. And also for full text searches, where we see things where we want to be able to search for keywords within large blocks of text. It may not be ideal to store that text solely within a database and retrieve it, one column at a time. Instead, we can use full text indexes to further define the data within large blocks of text to quickly find where one keyword may reside in multiple documents. We can see this in full text, or not full text, but search engines, which scrub the internet and go from web page to web page and store that web page in a network type model, where the top entity is a domain and the child entities are each document or each web page stored within that domain. And your full text index goes through and searches each document within that database and produces a list of keywords and where those keywords exist within certain documents. Can be so these application-specific databases and models can have significant improvements over traditional relational models. Now, for our software selection, It's largely dependent on what we're going to be using our database for. Certainly we can use many of the mature database management systems such as Microsoft SQL Server, Oracle SQL Server. These database systems are usually allow you a certain level of confidence in the system working the way it should, and often works with a maintenance and warranty contract with the Microsoft and Oracle companies, where if you need advanced assistance, it can be defined as part of a business contract between you and the vendor. That type of setup can be very important when you're working with critical data sets such as financial data, where you need to ensure that you're going to have data integrity and transactional safety. And if anything goes wrong, you have a certain level of you have a agreement with the vendor to perform a certain level of uptime and maintenance on that database system. Now, however, this may not be really what you need if you're working off a say a simple blog engine where all you really need to do is store a certain type of data and don't need that transactional safety. So you can often go with a NoSQL alternative, and NoSQL is usually defined by its how it stores data. So far in this presentation we've talked about SQL systems, which store their databases in tabular format. NoSQL databases, however, store their data in a wide variety of formats, such as through those XML documents or JSON documents, or wide columnar format, such as with Google's Bigtable. And these can have, certain levels of improvement over traditional SQL and relational database models, and may be useful for certain applications. And what I have here for transient versus persistent storage is how your database is going to require its data to be available. So, for example, certain blog engines may have their data stored in flat files, and when the application is initiated, it takes those flat files and stores it in memory in persistent and transitive storage, and the database itself is entirely within memory. And in addition to that, we also have how your data needs to be distributed. So we have replication, which is commonly it's your common distribution between relational databases. You see this in Microsoft's SQL Server, Oracle, MySQL, Postgres, SQL, and so forth, where the entire database is stored on a single system, and updates and inserts and deletes occur on a single system, and then those changes are replicated to other nodes within a say, a cluster of servers. The problem with this, though, is that when your data scales, you have to scale these servers up. So if your database becomes larger, each SQL server needs to have a larger hard drive. Now, an alternative to this is distributed file systems, such as Apache's Hadoop, or how Apache's Cassandra uses JSON files to distribute its data. These systems, instead of using database replication, well, they still use replication, but they use it to distribute data equally between the nodes in the data cluster, so that as your data scales up, your servers scale out. So if you want to improve performance and increase the size of storage, you can add additional servers, and the workload on that database is extended out to those servers. And then these database systems use a system either such as MapReduce or through Cassandra's similar system that perform two operations. They perform the map operation, which combines all the data within the cluster, and then the reduce operation, which is your query, such as saying, I want to see all the students, which will define your map operations, and then your query would be, I want to see all the students with the grade point average above 3, and that will be your reduce. Now, like we said, we have application-specific models. We also have application-specific software that uses those models. Like we talked before, key value system, key value caching, which is useful for working as a middleman between the database and the application. The example we have here is Redis, which not only allows us to define a key value cache, but also one that's semi-persistent and also distributed among your application servers. We also have Lucene here, which is a full text indexing software. You'll see this used in search engines, also web crawlers. The last one we have here is Bigtable, which is Google's denormalized storage system. This works on top of their distributed file system and doesn't normalize their data, but like we talked before, that denormalization gives you a performance increase when you need to quickly search through that data without having to perform large number of join operations. And the last thing we're going to look at is object relational mapping. Pretty much all programming languages that interact with database management systems need to do object relational mapping in some form. So this occurs when a database or a programming language is an application queries a database management system, pulls a data set or the results of a query from a database, and then needs to perform some sort of operation on that data. Often a ORM, object relational mapping framework, will be used. .NET's ORM, well, one of them is Entity Framework, And this allows you to interact with a wide variety of SQL database systems and NoSQL database systems to pull data and map it to a object within .NET, which is a object-oriented programming language, at least for some of the languages within .NET, such as C# and VB.NET. Two other frameworks we have here is LINQ and Corba. These are not object relational mapping systems, but they are often used in relation to a ORM to perform operations on data that came from a database management system. So LINQ and Corba allow you to perform operations a lot similar to the SQL transactional language. So SQL allows you to do stuff like retrieve a data set according to a query. LINQ and Corba extend that same functionality to the programming languages itself, so that data stored within a application's memory that's in a relational format can be queried as if it was relational data. That concludes the presentation. Thank you for listening.